Okay, I'll turn things over to Ron for an intro.
Okay. So obviously it's ridiculous to introduce Oscar because he's become a good friend of GISS in the last 9 months. Oscar is a master's student. This is the last part of his intern to come to a foreign lab for 9 months. We have some administrative problems because Columbia, it seems like they don't really go through this process very much, but we finally got it over here. I've been incredibly grateful. Aside from being obviously super smart, you are very curious. You have a lot of initiative, and you're very friendly. It's a real pleasure to work with you. So about 2 weeks from now, when you're back in France, I am going to look out the window or walk by your office and realize that you're not here anymore, and I'm going to feel sad. But anyhow, so this is, he's been working on really on a number of things that he's going to describe here, having to do with dust. As he'll explain in detail, we have some biases in the model we've had for a long time, and he's been looking at a number of ideas, both using observations and the model. So, Oscar, I'm going to let you take over.
Thank you, Ron. Thank you a lot, and thank you for surprising me throughout like this past 9 months. It's been really a pleasure on my side as well. So I'm going to present you what I did here at GISS. It's really concerning like processes controlling downwind transport of African dust aerosol over the Atlantic, and it's really focusing on what Model 2.1 is doing. So I'd like to give a special thanks to Sarah Smith for helping me with the CALIPSO dataset, Mark Spiegelman for helping me with the numerical schemes, and then Kostas Sigaridis, Mike Skibby, Peter Reddy, Damian Ringenstein, and Andrea Clarkson for helping me with navigating, modeling, and discovery in general. So, dust is the subject of our study. It is an aerosol. It's one of a very prevalent aerosol. It represents 70% of the global mass of aerosols on Earth, and it's contributing for 25% of the aerosol optical depth. It is emitted with a process called subtation, which is related to wind speed on dry riverbeds and lake beds. It's mostly concerned deserts, so like the Saharan desert, Arabian Peninsula, and the Central Asia desert. They form the dust belt, which is responsible for most of the emissions. If you look at dust, like the particles themselves, they have one. So here we can see that many pictures. One important specificity of dust as an aerosol is it comprise of very, very large particles, much larger than what aerosols are usually. So here are all the examples about like 100 micrometers, which is quite a lot for aerosol. Another thing to notice here is that it's not extremely spherical, and that's something to keep in mind going forward. So because it's very large, there is subcategories of aerosol classified in fine, coarse, super-coarse, giant modes. And in this study, we're going to look in particular at coarse and super-coarse aerosol, because giant is not in the model, and fine mode doesn't have the same biases, let's say. So what is dust in modeling? What is the importance of dust? So here, especially, this is presenting for coarse dust in particular. So you have multiple effects. You have the direct radiative effect, just being a very prominent aerosol. Then you have all the interaction with clouds, which can lead to precipitation or to nucleation, and this is contributing to the indirect effect of dust aerosols. But then you also have an ecological role. It is transporting nutrients like iron and phosphates. It can both like just ballast it in the oceans, so it reaches like the whole like depth of the ocean, or it can bring it to other regions, like the Amazonia, for instance. And then you also have it is a very present species, so it can react and play parts in atmospheric chemistry. So in the model, how does Model represent dust? It has to make assumption and parametrization. So first, one important one is watch out the different size categories. I think it works with bins. So these are the 5 ones that I've used throughout my stay. The SIL5 is somewhat implemented, but I did not take a look at it. So you have clay that is representing the fine aerosols, and then from SIL1 to SIL4, you have like different ranges of sizes. Once again, keep in mind that SIL3 and SIL4, the largest one, are maybe what we are going to take a deeper look at. For modeling, we have 40 vertical layers, and most of the dust is located in the 21st layers, so it's only a 20-layer resolution in a way. The horizontal resolution is 2 degrees by 2.5, we're using the HOMA configuration. In terms of emission, I talked to you about saltation. Saltation is parameterized in modeling using the surface wind speed. And once you have emission, you have two things to take care about. It's which one of each category do you emit more or less, and then how much do you emit of each of dust in general. And for this second parameter, it's a global scaling of emissions, and we're using Dust Optical Depth averages to tune it. And then once dust is emitted into the atmosphere, it doesn't stay eternally, it needs removal processes. And you have three kinds, which are types. So one important one is wet deposition, because it is related to washout by rain, so it's dependent on meteorological conditions. And one important part of this removal process, it is not dependent on size, not at all. And then you have two other mechanisms that are called dry deposition. You have turbulent deposition, which occurs mainly at the surface, and gravitational settling, which is extremely size dependent by virtue of just heavy large particle falling faster, because it's following Stokes theory, and Stokes theory is the balance between the weight and the drag. So yeah, to deal with gravitational settling, modeling is using an upstream scheme and Stokes theory. So that's what modeling is in terms of representing dust. What is the genesis of this project? So it is mostly this figure on the left here. You have two parts. This is Castellanos et al. 2024. I think it's one who made them both. So the first one is representing the absolute deposition in modeling, the solid line, across its transport. So across the longitude, it starts mostly eastward and it goes westward. And here you have three sediment traps that are making observations, that are making measurement of absolute deposition. And so we can compare the model to these in-situ measurements. And something we can see immediately is that the deposition is too high everywhere. So that's one of the biases we're going to try to tackle. And then to go a bit more in depth with that, we have the particle size distribution, to represent with the three point below. So the x-axis is the diameter, and the y-axis represents which fraction of mass is attributed to each diameter. This doesn't give any information about the absolute values that we are seeing, but just a relationship between different sizes. And so what we can see is that here, solid line is the observation by the sediment traps. Oh, maybe it's more clear if I show the sediment traps here. So this is our main source of emission, it's the Saharan Desert. Here the Bodele depression is really the most important one, and then it travels westward through the Atlantic, and here are the sediment traps on 12 degree.
Is this in the model or in the sources, like the location of the sources?
The sources are prescribed by the model.
Okay,
And
but
it's
from
also
observation, do you know that these are the two main sources, or?
Yeah.
Okay.
It's but then how exactly do we present the sources in the model versus the observation? So if we go, so we have three locations in longitude for each sediment trap, and we can see that even the closest one to the sources is still severely lacking in large particles. So all this white area here is things that are not captured by the model. The model is a red bar, so each bin size is one of the red bar. And for instance, SIL4 is almost inexistent at 20 degrees west and then completely vanishes here. So that one bias that we're trying to tackle. And SIL3, the category below, is also lacking when you go really far from the sources. Whereas SIL1 is quite present. To hammer in on this fact, you have here CALIPSO observations. And so here what I mostly want to show is that the slope of total dust optical depth as you go from east to west is much steeper for the modeling in black here, meaning that we're losing dust optical depth too fast as we travel along the Atlantic, downwind of the Atlantic, compared to satellite observations. Okay, so the particles, especially the large particles, the coarse and super-coarse particles, are not traveling far enough. So that's what we're going to try to investigate. So once again, this is our region of interest. Varies a little bit, but it's roughly from 5 degrees north to 30 degrees north and 60 west to 50 east, depending on how much you want to capture or not. For modeling, we did 5-year averages. We don't look at interannual variability. We did, so it's mostly annual averages with a bit of monthly analysis. And at some point, we are going to focus on summer in particular to look at the Saharan area, which is an important physical process. So what are the different hypotheses that we made with Ron to try to tackle this bias? There are 4 of them. The first one is the emission fraction. So I've explained to you there is a parameter that determines when do you emit some dust. But then how much of each category do you emit? There is different schemes, and the one that has first put in place was a bit simple, and now we have observations that allows us to get a more rigorous fraction of emissions. But that's something we're going to investigate. Then the site is very important, and we're going to use CALIPSO dataset, which has not been used to compare with MODELY for dust. And mainly the idea is that if particles get really high, or if they don't get really high enough, it will affect their lifetime. If we don't launch them high enough, they will fall faster in a way. They will spend less time in the atmosphere. Then one very important part of the study is the study of asphericity, because as I've told you and I'll show you on picture, dust particles are known to be very aspherical. And some paper suggest that it can lead to a reduction of the gravitational settling velocity by up to 20%. So we're going to try to put that in the model and see how it affects the mass load of dust and its particle size distribution with transport. And then lastly, I've told you we have a very simple upwind or upstream scheme for the gravitational settling. It is known to be very computationally fast, but it's also known to be diffusive and not very accurate. So we're going to try a higher order scheme, which is a Semi-Lagrangian scheme, and see how it could benefit the representation of dust and the removal processes that is gravitational settling. So to just go a bit deeper in the measurements that we're using CALIPSO dataset. We're using the L3 sky gridded tropospheric product. And we have 2 main benefits with CALIPSO. First, there is the Calliope LIDAR. So it gives information about the vertical repartition of dust optical depth. We're using a climatology from 2006 to 2023. And then the second main point is the classification algorithms, which allows the product to recognize dust, to flag some feature as being dust, using clues like region, altitude, and polarization of the light. So we don't need to do it ourselves. That's very helpful. Something to keep in mind is that CALIPSO is known to be biased low versus aeronet measurement. So maybe we're going to find a little bit less dust optical depth. And then a very complementary dataset is the sediment traps by Van der Does. They're presented in these 2 articles. Why do I say it's complementary? Because it measures particle size distribution, which CALIPSO doesn't have access to, and it measures absolute deposition of mass, which is also something that CALIPSO doesn't have access to. So hopefully, looking at these 2 datasets, we can have a clear evaluation of MODELY's dust transport. So for MODELY, I've used multiple experiments, and I've mostly played around with 2 parameters. So the first one is the emission scheme. So the name doesn't really matter, but we have IM equals 0 and IM equals 4. IM equals 0 was what was in the model. It was a choice made for simplicity that was assuming a uniform fraction of emission. When you have emission, every size category is emitted in the same manner. But then there was an observation, and there was a more precise emission scheme that's called IM equals 4. That is skewed towards very large particles. So we are hopeful that if we emit more large particles, we will find more large particles downwind. Then the second parameter is what I call RSV, or reduced settling velocity. We explore 4 hypotheses, 4 scenarios. These 2 first ones are backed up by articles. So Hong et al. 2020 suggests 15.4% of reduction of settling velocity across all sizes, whereas GNU 2003 is using a size-dependent calculation for asphericity, meaning that each size category in Model E is going to be reduced by a different amount. And like, for instance, stage 4 is going to be slowed down much more with 20% of reduction compared to clay that is barely not changing its gravitational settling. Yeah, something that is important is that gravitational settling is much more important for largest category, once again. And then we also explore two scenarios that are not physical, that are just to see how much reduction we would need to match observation, maybe. So there is a 50% reduction here across all sizes and an 80% reduction across all sizes. We keep the global emission of dust consistent throughout the experiment, except one where we try to match with the CALIPSO Dust Optical Depth. All right. So for the first hypothesis, it's the emission fraction. Here on top, so it's the same plot with the particle size distribution across compared to the sediment traps at 3 longitude, going east to west, percussion spot. Here's the first one, so in-dust equals 0, uniform mass emission, and in-dust equals 4, so the more, hopefully, the more precise one. And I think for 23° west, it's very clear that the size distribution matches much better in the second scheme, the more like measurement informed scheme. So we're still missing a lot of SIL4, even at 23° west, but the three other SIL categories are matching better, and clay is still a bit lacking. And then if we go along with transports, we are losing completely SIL4, which is still a bit of bias, and we're losing also a bit of SIL3. But overall, it's much better than the previous scheme. So going forward, we're going to only use in-dust equal 4 for our emission scheme. Now let's take a look at dust height. So here is the comparison of the CALIPSO measurements in our region of interest of dust optical depth per layer compared to Model E. So the idea is we get CALIPSO gives the extinction coefficient, and we're just multiplying that by the height of each layer. So we get DOD per layer. And then we rescale the Model E results that are only 20 measurements on the 12 kilometer. That's why we have a stacked slope. So if we look at that, what can we see? We can see that the shape is a bit different, and we're not capturing necessarily the vertical distribution as well as we might have hoped. The black line is the one to look for the baseline arc control scenario. So the dust optical depth is more located in altitude, and we have a bias below 2 kilometers where we're missing dust optical depth. And then above 6 kilometers, CALIPSO yields no dust optical depth, whereas Model E still has some. And I think this is because of the fact that the numerical scheme is very diffusive. So it keeps a bit of particle high. Then we can, as a sort of sanity check, we can look at this paper from Drakaki et al. 2022 that is also comparing CALIPSO dataset that is called here LIVAS pure dust to another model that is with more like vertical layers. It's a go-kart model, and we see a same kind of bias with missing dust on the bottom parts and a bit high tail that is a bit too high. Then coming back here, if we look at different experiments, here in orange is the experiment where we rescale dust globally to match CALIPSO observation of DOD. So it fits a little bit better, but it's still too much. And then to try to explain this sort of general shape that is elevated, whereas CALIPSO is not so much. We're looking at particle size by particle size location of dust in terms of concentration. So it's not dust optical depth. So one thing that is very important to note is that the smaller a particle is, the more impact it is going to have on dust optical depth. And we see that there is a very strong gravitational sorting of the particles. So clay and silt are located more in altitude toward like 3 kilometers, whereas silt, especially the dash scenario, which is a control scenario, is really located towards the surface. It's really bad, not bad, but yeah, skewed towards the surface. So when we combine all of that together, like the concentration doesn't have like really a bump, but the DoD contribution has a bump because only the smallest particles are located in altitude. And so I think if we look at here, Ryder et al. 2018 is an aircraft campaign. And I think the mass fraction as a function of altitude, I think it shows that there is a bit more mixing up of all the different sizes of dust in altitude. And if we can capture that, maybe we will have a less like elevated DoD in the model.
I have a question. For the previous slide, have you looked at IM dust 0 and evaluated how the profile looks like?
Yes, but I did not show it here.
Okay, but it's not
better.
yeah, okay.
It's yeah, you have like the DoD is also much higher in general. We need to rescale to keep meaningful comparison. Okay, so then to sort of check if we're like maybe putting dust too low or not, we have hourly outputs of MODEL, and we have, I think the important idea here is to compare the dust elevation with the height of the planetary boundary layer, which is represented by the solid line here. Because we know the planetary boundary layer gets really high in the summer in the Sahara, and we want sort of the dust to be located, like it's supposed to be driven by the planetary boundary layer, and that's sort of what we see here. We see the dust is like in general it's mostly matching well with the PBL height. Another important thing to note is this sort of concentration here that is completely elevated. This is what is called the Saharan air layer. It's a hot air that is split on top of the marine boundary layer, and it's a very known phenomenon, and it's very nice that we can see that MODEL is capturing that. So it sort of suggests that MODEL is not wrong with the dust height, but maybe more wrong with the particle size distribution. Also, here is a SIL4 category, and we can see that it's, once again, the concentration is mostly located at the surface, and it's falling very fast. Like in a few hours, it's gone mostly. And then I will quickly talk about like seasonality of dust height. So this is the same plot as here on the left, but comparing just the regular IM Decibel 4 experiment with CALIPSO across all months, so since January going all the way to December. And we still have the Saharan layer here with elevated dust. And a little bit here, like you can see a sort of bump that we are assuming is a layer for CALIPSO. The thing to note is that, yeah, it's a bit more complex than just an annual averages. We have like some months where it matches pretty well with CALIPSO, and some months where it's completely much more off. And also like the season are a bit offsetted. So we have some months like January where CALIPSO is much higher than MODEL, and some months at the end of the summer where CALIPSO, MODEL is still sort of in summer mode with like a high concentration, whereas CALIPSO is already having much lower dust optical depth. Okay, so now let's take a look at the asphericity and its effects on gravitational settling, and then the effect on mass load. So here is a control experiment I'm just equal for with just the mass load for all size categories, the total, and this is for each size category. So here we can see what we call the dust belt with all these three regions having most of the mass. And here we can see the contribution of each size. So SIL1 and SIL2 are responsible for most of the mass, whereas clay and SIL4 not so much. You can also see that SIL4 is located much closer to the sources. And then if we take this sort of plot and we do a subtraction with the experiment where we have reduction of settling velocity, we arrive to this plot. So here in red means that the experiment with settling velocity reduction get more mass of dust in the column, whereas in blue it gets less mass. First, the global change here of 1.75, the average change, represents roughly 3% of the global mass load. So it's a very small change in general. And this small change is only located for SIL3 and SIL4, which is what we expect. We're slowing down more the particles, and they're the one that are driven mostly by gravitational settling. So this is where we see the most change. Especially for SIL4, we have almost like no blue regions, so the mass load increases everywhere. Whereas for clay and SIL1, it's actually like on average it's slightly negative, so we're actually losing this sort of dust when we're reducing the settling velocity. It might be surprising, but it can be explained because gravitational settling is not the only process of removal. Then if we compare if we want to take a look at the absolute deposition, so here are different experiments. So it's still very much too high. And then you can have two hypotheses. Either we're not representing deposition correctly, and so it affects deposition, but also the global load, the global scaling might be off. And I think these two have a different effect, because if these experiments are our baseline, if we scale all the emissions to be a bit lower, we have a sort of the same curve but offsetted down. It's a bit lower. But if we just reduce the settling velocity, then we have the slope that changes a little bit. This is the 80% reduction of settling velocity. It starts to the same amount of deposition here on the east, and then as you get more and more west, you're still keeping a lot of deposition because more particles are staying longer into the air.
By the way, Olivia implemented a new deposition scheme.
Oh, the turbulent
I
deposition.
assume is it in the simulations or
No, because she's using matrix and we're using OMA.
Oh, I thought it's also in OMA.
I think she tried it with OMA. That's kind of,
I
Yeah.
think it might also be an OMA, because I know for OMA, the diagnostics, all the chart deposition got thrown into one. So gravitational
Okay.
settling changed, but I don't know exactly.
So
Anna would be fun.
potentially, a new simulation could answer how dry deposition affect.
yeah, so when I look at, this is the total deposition, but then I also can look at the influence of gravitational settling alone, right, when I do my different experiments.
Yeah.
But yeah, I mean, yes, I did not look at all at turbulent deposition, and then I also knew that Olivia did it already. So yeah, but I don't know which one is it in here, but whether it is here or not, it's consistent across all experiments.
Yeah.
I think with Olivia, so it's the turbulent deposition, so it takes place only at the surface. It's whereas, Oscar's looking at gravitational settlement really throughout the column.
Got it.
So that's,
There weren't any changes to that.
yeah, so also,
Probably small.
sure, yeah, so, but also when Yue was here, Yue Wang, who was one, we recommended a reduction of satellite velocities because of asphericity. I think she and Olivia got together and they decided it wasn't really having a big effect for dust particles.
Sure.
Yeah.
Sorry, could you remind me the difference between IM dust equals 0 and IM dust equals 4?
So here, all of that is IM dust equal 4. But IM dust equal 0 is when you have emission, you are emitting the same amount of each size category. IM dust equal 4 is when you are emitting more large particles from the beginning, right?
Okay, thanks. And no RSV is applied to both of them, correct? Or like there's
Different
no.
kind of RSV were applied to both of them, but then I'm only presenting IM dust equal 4 because it's a better scheme.
Oh, okay.
Okay, so then we can look at the lifetimes to sort of see the general, one more quantitative way that the RSV is affecting this lifetime. So the lifetime is defined here as mass load divided by the emissions. So it gives a time, and that's a sort of average time that the particle is staying in the atmosphere. So for the control experiment, it's staying 55 hours in average across all sizes, but it's 200 hours for clay because it's very small and light, and 10 hours for SIL4 because SIL4 falls very fast. And then if you look at the change, the relative change with for each experiment, so this one is our most physically precise experiment, and here are two physical experiments. You can see that it's not really linear. Like if we change like I'm saying a little bit, but still for GNU4 experiments, still 4 is increasing, is slow down by 20%, and it leads to a 30% increase of lifetime. But then if you slow down by 50 or by 80%, like the relationship between the reduction of settling velocity and the increase of lifetime is not linear. The more you reduce it, the bigger impact it has on the lifetime. So for instance, the 80% experiment has a very like the total increase is like 40%, which is significant, and for still 4 it's really multiplied by once again by 172%. So this suggests that we would see a bit of bigger effect using 80% of reduction of settling velocity, and so we're going to take a deeper look at that, even though it's not physical. So once again, the same graph with the particle size distribution compared to the three sediment traps from east to west. And here's our most like, it's the GNU experiments, so the sort of physical reduction of settling velocity versus the unphysical but higher. And what we can see here is that for once, the SIL4 category, which is the largest one, is matching quite, yeah, as a very good match with the observation measurement, with the Van der Does in-situ measurement. And like the overall distribution for the silt is very good. For the clay, it's completely lacking. But for the silt, for the larger particles that were the subject of the study, it's matching very well. And it's also consistent when you go downward of the downwind of the Atlantic, which is really good. But it takes 80%, and 80% is once again unphysical. So just to give an idea, if we're using still the same theory as GNU, we would need an aspect ratio, so the relationship between length and width of 5 to reach 60% of reduction of settling velocity for 20 microns, and we will need an aspect ratio of 10 to reach 80%. So how close are we to these values? Not at all, because the estimated aspect ratio is around 2 for those particles. But then we also could have the hypothesis of only the very aspherical particles are traveling far, and so then we would have a bias if we do measurement far from the source. So that's what Yue Huang did in her paper in 2020. She's defining different in-situ measurement as sources, short-range transport, and long-range transport, and she's calculating the median aspect ratio for each of that. And what she can see is an increase as you get further and further away from the source. But it's not going from 2 to 10 or 2 to 5, it's going from 1.6 to 2. So it's not enough to justify an 80% of reduction of settling velocity. But it's something to keep in mind. If we want to get particles to get further away, we might need to overestimate the aspherical effect a little bit, just to express the fact that some particles are very aspherical and they will get further away.
So another question for that figure, is that assuming consistent RSV across all the different particle sizes that the RSV?
What is this experiment? Oh,
Yeah.
This plot is in-situ measurement. There is no reduction of settling velocity.
Okay, sorry. Okay.
But then also something to note is, once again, here this is not, there is no consideration for the size of the particles, but we know that the larger a particle is, the more aspherical it's going to be.
Yeah.
So that's something we
So I
should.
think what you're asking is like, if we reduce the settling velocity of each particle size by 80%, I think that's what we did, right?
Yes.
Yeah. So it was a uniform reduction.
Although 80% it's across all sizes.
Yeah.
Okay, so sort of the conclusion that we can have here is that we need something very a bit unphysical to reach a good match with the observations, and yeah, there is a balance between particle size distribution if you want to match, but then we would get less Dust Optical Depth, and so when we scale, we would get more deposition. So yeah, we have a bit of balance between the three. Now I will sort of change gear a little bit and talk about the numerical scheme, which is a bit like, yeah, very different from, it's sort of second part in my internship. So the upstream scheme is what we currently have in ModelE, and what I've investigated is the Semi-Lagrangian scheme. So that's our two numerical schemes. So to explain a little bit how they work, on the x-axis is different time. So we have, I think, like one time step. And here is a vertical grid of the model. And the idea of the upstream scheme is you have a speed of calculated here for this level, and you're just going to take this speed times the time step to define the length and get a fraction of the mass here, like which corresponds to this like sort of gray area, and you just put it to the grid box below. So doing that, you're making two assumptions. So first, you're like using the speed here and not the speed at the boundary, and then you're assuming a uniform distribution of mass in the grid box. So this is why it is expected to be not very accurate and very diffusive, but also the way the scheme works makes it positive and conservative. So the mass, we know that the mass that is leaving this grid box here is going to be exactly the mass that arrived here, and so there is in the column. We have the Semi-Lagrangian scheme, which is higher order. So the idea here is we have set the vertical grid points here, grid points, and here on the bottom line is the different time steps. The idea is that the mass at this grid point, it comes to follow the trajectory, and this is this trajectory here with the solid line. And so if we get the mass exactly, if we get what the mass is at this point, at our current time step, we can just say that the mass here is going to be exactly the mass that reaches this point here. So we need two approximations. We need to approximate this trajectory, and we need to approximate the mass at this point. And so we have a way to do that using the speed, the gravitational settling speed. And that, once again, we need two interpolations, one for the speed and one for the mass. So using two interpolation, of course, it costs a little bit more, but it's going to be more accurate and less diffusive. But then one problem is that this is not inherently conservative or positive. When we do interpolation, sometimes we can get negative mass. But the main problem is the conservation, because if we run the model for a very long time, even if we have a small problem of conservation, it's going to grow and be bigger. So there is a trick, and thanks to a paper by Lentin, we could make the Semi-Lagrangian scheme conservative. So going forward, we're going to study a conservative Semi-Lagrangian scheme. We're going to evaluate this conservation. So let's take a look at how I compare these two schemes. So instead of putting it directly into the model, I did a single column model in Python using the grid boxes of the model and using basically the same structure as the model, but I did it in Python on a single column. I've explored two scenarios. One where it's just an initial source of that is a Gaussian distribution, and we let it fall in time. And the second scenario, we start from with no mass, and we just at every time step we inject a little bit of mass, and we reach a steady state. So for these two scenarios, I did one case where we have a gravitational settling velocity that is varying the column here with the gradients, and one with no gradient. We can find the exact solution accuracy this way. So what we the dashed line is the analytical solution. The black line is the conservative Semi-Lagrangian scheme. And behind is because of once again the so then like how much can we error that we can find this way? And so for our different scenarios, once again you have the orange that is the scheme, the black that is the conservative Semi-Lagrangian scheme, and in all cases, these two cases we have a much better accuracy. We have less error in the conservative Semi-Lagrangian, which is good, which is what we want. Here, in this case, we can compare to the exact solution of the steady state. So that's why the error starts high and then gets a constant value. And so I mentioned that we need something conservative, so I've just make sure that everything was conservative. So for that, you get the total mass at a specific time. You subtract the mass of the at the initial time. And what is remaining is only the contribution in time of all the sinks and all the sources. For us, the only sink is a flux of what is deposited at the surface, and that's something that we need to estimate properly. So this error should be 0. If we calculate that, it should be 0 all the time. And what we can find is that in every experiment, it's not 0 because we have a shrinkation error, but it's to the power of -14, so it really only relates to the finite number of bits that we can save information in. And the conservative Semi-Lagrangian scheme looks like it's a bit higher because I think there is just more calculation done, so you have more accumulation of truncation error. But yes, I think this can be considered fully conservative because we won't reach the time scale where an error of conservation of 10⁻14. But once again, I didn't solve the positivity problem. If we want to force it, it might be not conservative anymore. We can also look at other higher order scheme. Okay, so to conclude. If we get more observation of the particle size distribution at emissions, we might get an even more faithful representation. Dust height, which was interesting, we saw that there is a vertical sorting that might lead to problem when like looking at 5. But we are capturing a lot of physical processes, so it matches with the PBL height, and we are getting the Saran area. In terms of setting density and asphericity, if we do something that is improvement, but it's a very small improvement, and then the aspect ratio that we observe are not enough to justify a much stronger improvement that would have a very significant effect. And then, so lastly, the numerical scheme, as I've explained, like I did this sort of simulacrum in Python, but we would need to put it into the model to see if it's how much it affects the deposition. But we definitely were using a very diffusive and not accurate scheme currently. To sort of conclude this presentation, I think one thing that is important to note once again is that I look at like 3 positions, the Dust Optical Depth and the particle size distribution, and it's hard to find a balance between the 3. Yeah, so I think one way to sort of investigate the tense would be to add more clay. We show new numerical scheme we are a bit lacking in terms of clay, but if we add more clay, because it's very small, it's going to have Dust Optical Depth, which means that reduce the global emissions of dust. We've shown that it will have much less absolute deposition. So it will be a way to sort of find a better balance, more clay. But what physical process would like us to add more clay? I think to look at wet removal because that is the one that is responsible for the removal of clay. So yeah, wet removal. I did not do it here. And then this like a convection, small scale convection. It's going through multiple. You relaunch, like even if it's flying fast, if it's relaunched like regularly, it's going to reach a much like longer distance, and it's going to be. And then we have also it here. And CALIPSO is now out of business, but we will have new satellites and probably worth to check them. Yeah, thank you.
So if anyone in the room has questions, or if you're online, please feel free to mute yourself. I'm also sorry online that the video cut out. The owl is being a little finicky.
Um, how do you expect that things, given that, these changes?
And G3, so I mean, she's asking me this question. From the model that you haven't seen at all. And I haven't seen it either, but I think we have better. We're initially running matrix, and so we have explicit coupling of aerosols to the cloud microphysics, and so deposition might be what deposition is going to be more mechanistic. So I think actually, just segue back to one of your last conclusions, you wanted to do a better job of what deposition E3 might be. Try to make sure we were doing something that was physical. So sadly, you will be start running E3 after possibly. But that is that could be something. I mean that's it's coupled with aerosols, and so instead of using
just specify like that's soluble in water, and that is really what kind of dominates what gets removed with wet deposition. So is Dust the same thing? And if it is, have you compared your solubility properties or anything?
So.
Or is that like not all?
Dust is very, like, very insoluble. But then how, like, I never changed this parameter, right?
Okay.
So, I think. Like, definitely there's something because, when you're the emitter and use the, it has been like, increased by the water content.
Yeah.
So, also maybe, if you're wrong, I mean, I think for Dust, like, there is no change of the emitter with water, but, that's something to investigate, I guess.
But it is fixed in the way that Maggie.
Cool.
So probably a good strategy going forward would just be to start changing that fixed fraction. Watch out. Like Karen says, we will have explicit cloud microphysics and aerosol microphysics coupled. Actual physics as to what. So.
Any questions?
When you were looking at the numerics, I think maybe the plots said like you had like a size. Or
Yes, so
if you consider the error from like binning, is that kind of dwarf? How does that compare to like having size, kind of large size bins?
So, so in Python, what I did in my single-bone model in Python, I've explored a little bit different how fast there is. If you just like the gravitational settling, but I see changes in behavior.
I don't exactly remember your bins, but you have a single bin for like 30 to 60. Does that I'm just wondering how like that uncertainty might compare to this.
Oh, okay, the fact that we're using
Would it be
diameter for
like
yes, I don't exactly know like the impact of building on the numerical scheme. Diameter, right? But
yeah, I guess maybe just as like a context for this error. I was wondering.
I think we have an effective kind of cross formula that we use to calculate how fast these particles. And what makes it effective is we're attempting to look at the continuous variations within the bin. But, as you say, we had, the wider the bin gets, then the less that.
I guess I'm just wondering how that bin descriptive would compare to the like upwind scheme.
It's hard to know. We actually, as a model, among our system models, we have a relatively high number of bins.
Yeah, yeah. I'm kind of shocked actually. The clouds.
So, yeah, I guess, one thing we can do is just, try to like multiply it by, the number of dust bins.
I think it's kind of like, it's like our specificity, we to choose one specific aspect ratio and work from that.
Right.
But actually, there might be a whole range of different aspect ratio, and if we take only, like, we can take a parameter that is more related to, there is an error associated with that.
I feel like I've learned a lot and I don't know anything about aerosols or anything, but, so. I'm curious about the Semi-Lagrangian scheme. You were talking offline yesterday about how you mostly do, it's a quadratic, is that correct?
Yes,
Yeah.
it's equal for the mass and for the but you can go higher order. It is possible, but with a sort of custom recipe to make it conservative. It only works for linear and quadratic approximation of the mass.
Sorry, what? It only what?
It only works for linear and quadratic interpolation of the mass. The recipe that I'm using to make sure the scheme is conservative.
Okay, so you haven't looked at like.
So I've looked when I did the first experiment with a non-conservative scheme, and I look at cubic interpolation, and it's a bit more precise. So if you look at this error, for instance, it would have been half another. Being non-conservative leads to a lot of. Yes, I don't think it. I mean, it's worth it at all.
Thank you.
This is maybe a meta question, but as someone who seems to have made a lot of progress using Model-E in 9 months, do you have any advice for aspiring Model-E developers?
Just ask for help. Not gonna be loud, I have to do that.
That's very good.
And I mean, you have some very important things that you know how to look in.
With Mohammed and Zachary and Maggie, but yeah, I think probably that's something that GISS needs as a whole.
So not just the early career people.
For whoever feels like it's a struggle.
Yeah.
It's cost. But yeah.
Like a good first step. Maybe Ron mentioned in your intro, I dumped out to get pizza, but
Back to France,
Right.
yes, I mentioned that. I'm going to start my PhD. So exciting.
Will you work on that or you don't know?
I will work on aerosols, but not just, we'll work on mixes of aerosols.
Oh, nice.
very cool. Okay, I think we're good on time, but if there's not any more questions, then we just give another round of applause. Yeah, we'll stop it here. But how much longer? When do you officially leave?
Well,
Oh, wow.
Literally.
Yeah.